let's begin. Question number 6. Let's move it to a whiteboard, please, and let's begin on it, okay? So let fx be this thing, this function, blah, 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 and show that blah, blah, blah. Okay, let's start things off. This is, they want you to express fx in partial fractions. You know, while we did partial fractions. Okay, let's try how to do partial fractions. Huh? Okay, the first thing is, what we do is we write something like this. So, sorry, my handwriting. Okay, fx like that equals to 4x whole thing over 3x plus 1 and then x plus 1 squared. So the rule of partial fraction, there are a few rules which you can see from any standard textbook. So we're just going to show how to do it here also. So that means we do something like this. I think I should write below. Okay, let me write below. Okay, that's right. So what you do is you have to write it like a linear factor 3x plus 1. So a power lower than that is a constant. So 3xa over 3x plus 1. Then for this factor, x plus 1 is linear, but it is a quadratic. Okay, x plus 1 perfect square. So when it's a perfect square or quadratic, and it's repeated factor, so it comes under two conditions here. You must learn as you go along. So one is that it appears by itself as a constant bx plus 1. And just for the argument's sake, we need to put it as a repeated factor as well. So cx plus d, whole thing over x plus 1 square. So that means whenever we deal with a repeated, repeated factor, we need to think about the factor and a square. But then there's actually a bit of a modification, because when the repeated factor happens, because when you play around with that, they will cause the linear term. So this is actually kind of not correct, the cx plus d part. So in the normal quadratic, you'll put a cx plus d, but here you won't. The reason why, okay, this is rarely discussed, we just put a constant. Because if you multiply between the two x plus 1 square, just imagine, I just show that temporarily, and it's not necessary to know. If you put like that, you make the denominator same. Can you see you're just actually creating a linear there? That means a linear thing in the numerator, b of x plus 1 plus c, to rewrite into a linear factor. So actually, we're essentially just writing that. But because it's a perfect square, it is a special trait that it always can be proven to break down like this to just two constants. Okay, that's why the shortcut works. Okay, so now you know the meaning and why it is like that, more than just doing it. Okay, now we write it like this, comparing it to the earlier general form. Okay, we multiply throughout by the denominator. So a will have a x plus 1 square beside it. And then b would have a 3x plus 1 and an additional x plus 1 with it. While c would only have a 3x plus 1 with it. Okay, 3x plus 1 like that. Okay, now we just need to select some careful values. Easiest way to do it would to substitute some careful values to get the values of a, b, c respectively. So let's start. So normally 3 substitutions would do. Let's put x equal to, how to zero the expression sum of it on the right. So x is -1 by putting x plus 1 equal to 0. That's the logic. So you would get 4x equals to, this is 0, a plus 1 is becomes 0. So that means x plus 1, sorry. These two terms vanish. So only got c, and then, sorry, what am I writing? 4, -1. 4, -1 like that. We've got a c here. 3, because the x plus 1s become 0. So 3 of -1 plus 1 in bracket. Okay, repeat that. 3 of -1 plus 1. Aha. So we have -4 here equals to, what is -3 plus 2 is -2, -2c. So finally we realize c is 2. Okay, one value gotten here. Let's try to do the second value just beside it if we can. We put x is -1 over 3. That is to make 3x plus 1 0. By putting 3x plus 1 is 0, you get it actually in reverse. By solving that, x is -1 over 3. So let's substitute that place. So on the left-hand side, 4 -1 over 3. Aha, whatever with 3x plus 1 vanish, yeah? So 0, 0, the b and c. So only got this a thingy. So a becomes, so a, this is -1 over 3 plus 1. square. Don't forget the square, please. So negative 4 over 3, then just multiplied by, just simplifying the bracket, you can see that this becomes, it's perfect square there. 4 over 9, 2, 3, yeah? So that means when you multiply 4, 9a like that, so 9 over 4 just to get the value of a. So in other words, a is negative 3. You'll notice that a is negative 3. Okay, please take note. Okay, now how about the value of b? So we just need one more suitable substitution. Take something that is easy, something like x equal to 0. Okay, so left hand side become 4 times 0. Just become a 0 plus 1. Okay, just show this part, a bit more clear. So it's like a 0 plus 1 also. There's a 0 plus 1. A lot of zeros there. Can you see what the suitable choice would make it easy? Other numbers would give the same answer, but simpler calculation. A is negative 3. Aha. The b we don't know. This becomes b in the middle because 0 plus 1. Okay. This and plus c, right? C is 2. Ta-da! Okay. So then we solve for the value of b, which is 1. Okay, b is 1. 3 minus 2 or 1. B is 1. So a, b, c like that. So therefore now the partial fractions, we can write it as so fx, just put in back the values, please. So negative 3 over 3x plus 1. The b is what? Correct, huh? Just double check. The bracket, sometimes just for emphasis. B is 1, sorry. Let's get confused. Okay, x plus 1 like that. And then the c is 2. So 2 over x plus 1, whole thing square. Please don't expand it. Done. This is the part 1. Express it in partial fractions. Okay, expressing it in partial fractions. Okay, and then now we're going to do for the second part. They say, yeah. Okay, how do you do the second part? Okay. Everything correct, huh? C is 2, right? C is 2. Yep, C is 2. Okay, so so for the second part, what I need to do is just need to do some logarithm. So let me just take this this image only and clear the screen so it's a bit more clear. Thinking of cutting the image. Ta-da. Okay, now it's okay. So fx, please take note there's fx. So let me clear the screen and do the second part, please. So just confused for no reason. Okay. Okay, there's an F there. Okay, so we need to use the first part. Sometimes they won't mention that, but please understand that by the question itself. So we're doing the second one. Ta-da. Hence show that. Show that. So integration of fx from 0 to 1 dx is going to be this thing. So we're going to show that. So the amazing thing is we just copy the blue one first. So 0 to 1 integral limits, definite integral. So let's just copy first. Each of these can be separated. Okay. I'm just going to write like this, separate them out. Sorry. 3x plus 1. Just thinking, changing color and writing this one is confusing me. Okay, 0 to 1. Put a dx like that. Plus 0 to 1. Dx at the very end. Okay, so that means this becomes 1 over x plus 1. And this one becomes actually wait, these two, because you know why? Because there's no real formula for the x plus 1 square by itself, and then the numerator is should be a linear. That means what we do is we do a bit of algebra. Sorry, my mistake on that. I'm doing it like that. Sorry, see, let me just change this first. That means if you're wondering what am I talking about, these two, we combine these two, please, to get it in a particular form. That's the reason why. So 1 over x plus 1 plus 2 over x plus 1 square would equal to x plus 1 plus 2 in the numerator, making the denominator same. That's the trick. Please take note. X plus 3 over x plus 1 square. Why do we need to do this? Why can't I separate it? Because you must understand the formula, underlying formula we're using looks something like this. F prime x over fx, the integration is defined based on discovery of formulas, by the way, in case you didn't realize. So modulus of fx, modulus to ensure that the log is defined, plus c over range that is defined. Got the constant, I'm doing a full indefinite integral. But the fact is, the ln fx part, the ln fx only works if f prime x over fx, that form. So if you look at this one, it doesn't have that form, because you differentiate a quadratic, you'll get a linear 2x plus 2. So we can't do it by itself. This one still can independently. So what we do is we combine the two terms with a denominator. Small trick there. So algebraic small trick. That is why I rewrite this part as, so it becomes x plus 3 over x plus 1 whole thing square. So it's a very clever question if you notice that. Integration is already based, technique based. Okay, to discover that method works, then you must identify correctly. So now if you look at it carefully, if I were to write it like this, see the differentiation, that means the f prime x of the 3x plus 1 is 3. Can you understand what I'm talking? Okay, so yeah, meaning that if we take this as fx, we just put a note here, like a note way of doing it, taking how to write it in a nice way, but I think without making things complicated. So the f prime x for this part, differentiate the denominator, you get 3. Aha. If you do the f prime x for this flour, if you notice, it's a bit more fascinating. F prime x for this flour, it becomes what? It becomes 2x plus 2, isn't it? 2x plus 2 is it? Aha. So how do we account for that? So how do we account for that? So we don't have a 2 there, and neither do we have a, have a this thing. So how do we link that? 2x plus 2. Is there a suitable constant that we can take out? So it can make the whole thing the same. Okay, let's think and see. Oh, sorry. Wait, let me think and see. The ln of x plus 1, right? Ln of x plus 1 square. I'm still thinking about it. Another form. This. It is oh yeah. Actually, what a silly thing I'm doing. Actually, it's not even in the log form one. We can just integrate it separately. I think I just made a whole blunder, because then I realized that it's not in the exact form. Only if the constant match we can use that. Meaning that this can just add the power 1. Okay, I don't know why else. Yeah, just got lost in that. Okay, sorry. I realized. Okay, been a while since doing this. Okay, sorry about that. Okay, so we go for 1 over x plus 1. Just separate out again as per the original. Means the original breaking down of the partial fraction is just perfect for this. I tried to combine the two, but it's not the same type, so we can't. So not an issue at all. We just rewrite it as 2, but I'm going to write it like this. This time I'm going to write it as a power form, minus 2. The power is minus 2 because you can use that index thing in this. Okay. All right. So now this part becomes, it has that form, the log form, logarithm form. So that means it becomes ln of the modulus of 3x plus 1. And then let's put the integral limits on the box. But there's some -3 as well. So let's just move this right outside. A constant you can just copy on the outside. So this is -3 like that. This is a 1. This is a 0. Okay, okay, because there is oh sorry. There's only a negative sign. You know why? Because the difference when you differentiate is 3 1. 3 means we take the 3, only the negative sign is out. Okay, let me write nicely. Sorry. To think of it more accurately. Sorry, my mistake. Negative ln of modulus 3x plus 1. So the limit, integral limit is 1 and 0. Just the correct one. Okay, being that said, let's go for the second one, please. So second one becomes, let's put the integration box. So differentiate inside is still 1. So you get a ln of modulus of x plus 1. So from 0 to 1, the integral limits. Correct, huh? Let's take note. Okay, all these are correct now. The other one, that is what I was getting confused. I thought it must join like that. I was thinking, my mind told me that, but actually not. We don't need to. It's just an exponent, right? That means it's a polynomial exponent. That means like you can do a +1 and divide by -2 + 1. That's it. Simple as that. Differentiate inside is 1, so we don't need to differentiate by chain rule. And we just need to evaluate this as well under the integral limits of 1 and 0. Okay, now it's just a matter of calculating each part correctly. So let's do that, please. So when you put the ln 1 inside, so it becomes minus ln. Let's put the 1. 1, imagine put inside 3 times 1 + 1, 4. Minus, when you put 0 inside, minus, got a negative. Minus is one thing by the formula. Negative, so ln of, put 0, 3 times 0 + 1. Aha, ln of 1. Like that. And then the second one is 0 + 1. And then the second one is 1. So ln of, let's put this as 1. Is 1, sorry. Okay, so ln of 2, 1 + 1 is 2 minus ln of, you put 0, 1. So take and minus like that. It's a substitute. Please take note. So the third one here, okay, let's say we just do one step for this. It's a bit of arithmetic only, x + 1. So -2 in front got -2. This is -2 over negative x + 1 power of 1. So we're going to substitute 1 and 0 next on this. Okay, let's simplify this, please. So this becomes ln of 1, we just write first, minus ln of 4. So the green one becomes plus ln of 2 minus ln of 1. Then the third one becomes, when you substitute the 1, become minus 2 over 2. So -1. 2 over 2 is -1. Then minus, when you put a 0, becomes -2 over 1 or -2. Just carefully trying to evaluate. Of course, ln 1 is 0. You can use the fact that ln 1 is 0, or you can just cancel off. Doesn't matter in this case. Or sometimes you can use the fact log of any base 1 is 0. Any admissible base. Okay, so all we have now is, it's just part ln 2, minus the ln 4. Just going to change the ln 4 little. Please take note. Using the log laws as a 2 squared. And here, just put it as -1 + 2. Okay, and then go for the final blow. Ln 2 minus 2 ln 2. 2 minus 1 is +1. That's just like algebra at this point, where the final answer now appears as, right, the 1 first. This is like 1 minus -2 is -1 of the ln 2. So there we have it, QED, which was to be shown. And show that. So correct, there we have the answer. Thank you.